So the first speaker of the morning session is Adam Sikora from Macquarie University. I think I don't need to introduce you. Everybody knows you well. And he will speak about Hardy spaces and harmonic weights. Please start the talk.
Thank you very much for invitation. I'm sorry that I sent up my abstract so late. Actually, always kind of somebody explained me how to do it in Zoom that my face is not so black, but kind of like, I don't know. So you probably kind of have to leave for this lecture with me not quite well visible. And
I think it is your own camera. On my screen, your face is very well visible.
Okay, that's good. So I want to talk about Hardy spaces and harmonic functions or harmonic weights. So this is a topic which is with me for last probably over 2 years. Some kind of a bit of new development. So this is what I want to talk about. And so we investigate the Hardy spaces. So but the Hardy space is not a classical Hardy spaces, but as Hardy spaces corresponding to self-adjoint operator L. And we follow the general definition of Hoffman, Lu, Mitra, and Jan. And we assume that there exists L-harmonic non-negative function H, which is preserved by the semi-group, and such that if we apply dupe transform, which I will explain a little bit later, then this semi-groups will satisfy lower and upper Gaussian estimates. And under this assumption, we describe, we think, illuminating characterization of Hardy spaces H1L, for which atomic decomposition is associated with this L-harmonic function H, so for which we got condition of integral 0 against function H. So we've got a cancellation condition against function H rather than constant. So this is a kind of development in a classical and well-known theory of Hardy spaces. If we think about this self-adjoint operator L being just Laplace Bertrami, it just be the Laplace standard Laplace operator on Rn, then this space is actually just coincides with classical notion of Hardy spaces, right? So this is really a true generalization of these ideas. There are many applications of Hardy spaces. One of more important one is that Hardy spaces can be used to get, say, boundness extend boundness on L1. So usually, if we've got a singular integral operators, they are not bounded from L1 to L1, but they will be bounded from Hardy spaces to L1. So that's one kind of a point which has many applications and which kind of draws a lot of attention. Initially, Hardy spaces were defined by Hardy, of course, and it was defined in the setting of, in the question of asking of, say, boundary value of analytic functions on a complex disk, right? And you could kind of see how this definition evolved into a definition of Hardy spaces. So the 5, 6 or so major kind of equivalent definition of Hardy spaces. One is defined by corresponding, considering corresponding maximal operators. So we just take action of heat semigroup and we take supremum over time, right? And if this supremum, this maximal function belongs to L1, then we say that function f is in H1 and its H1 norm is equal, say, to the norm L1 norm of of the maximal function. So with a definition like this, so this is actually a classical definition for classical Hardy spaces. If we start from the standard Laplace operator, if you replace delta by any other operator, then you can kind of automatically, in a sense, extend this definition to some bigger setting. Of course, you need some assumptions, and there's quite nice general theory of such spaces, as I mentioned in a paper of Hoffman et al. So some another characterization. So you can characterize you can characterize Hardy spaces also using quadratic functions and losing area operators. So this is kind of like the difference is just between integrating over some cone here, right? So we can integrate over some cone here, right? Whereas here we can just integrate with respect to time, right? But this all kind of definition will lead to equivalent definitions, and even in case of weighted spaces, of Mackenhaupt weighted spaces, and of course, it's all very natural here to, with some reasonable assumptions, to study essentially any self-adjoint, say elliptic, subelliptic operators of that nature. So one, because I'm talking about cancellation conditions, so one here explanation that with with using Hilbert transform or Riesz transform, if you wish, you can characterize Hardy space by assuming that Hilbert, say, transform of function f is still in L1. So that's yet another definition, which, if you think about it, this implies that if function f is in Hardy spaces, then its integral is equal to 0. Right, so that's, and this is kind of equivalent with all other definitions. You can actually see here a little bit of connection with what I said, that this is kind of, initially it was related to Hardy asking about boundary values of analytic functions, right? So analytic functions, they will have only zeros for negative Fourier coefficients, right? So then Hilbert transform, in a sense, acting on these functions, will just leave them alone, right? So they will be automatically in this space, and there is kind of like actually some kind of a translation of this condition and this analytic assumptions here, but I don't want to talk about this one here. I just want to here to mention, right, that pretty much the continuity, once again, the continuity of Hilbert transform, if you think about it. So if you've got a function whose Fourier transform is not equal to 0, if you apply Hilbert transform, this means that you will multiply this bit here by -1, right? So then you will have a function which has a jump here, right? And of course, any function which is in L1 has continuous Fourier transform, right? So that implies that any function in a Hardy space has this condition f of x is equal to 0 integral, right? That shouldn't be infimum, this should be integral. Yeah, sorry. And so this idea leads to the idea of atomic decomposition, right, of Kaufman and later. And basically, we can write down any function here as a sum of atoms. So we've got here a number of conditions, right? So we assume that we've got series of function ak, right? And all these functions are supported in some ball. There is some size condition on these functions, and finally this condition ak of x dx has to be equal 0. So that's leads to definition. So this is kind of like, so the just assumptions that the integral of the function is 0 is not enough, and you can kind of see it clearly. I mean, I'm explaining this, probably all obvious for you, but we can think about, you know, functions which is, say, 1 here and -1 here, right? And this functions is essentially, if you look at this, well, I should maybe draw it this way, right? So you can think about functions which is like that, right? So, and this function is definitely in H1. There will be no problem with this. But then you can try to, you know, push these functions this way and that way as far as possible. So this kind of cancellations are far and far away. If you think about applying maximal functions to this one, then if you push them very, very far away, then this kind of like the cancellation between these two parts is coming from plus minus will come up very late. So actually it means that if we push this kind of function, if we push this -1 characteristic and 1 characteristic far away, then the HP norm, the H1 norm, will be kind of growing to infinity, right? So this is kind of like, and this is deal with here by this assumptions on the size and support, right? So that's, and if we kind of take this into account, then we end up with definition. So this is for a classical Laplace operator, right? And for classical Hardy spaces. And then there is a nice, very interesting kind of very important results of Hoffman, Lu, Mitra, and Li-Shin Yan, which describe abstract definition of Hardy spaces. And this pretty much all this kind of equivalent conditions from classical theory are here, except that definition of atoms are somehow less explicit, right? So we don't have atoms just by cancellation conditions, but we have to assume that atom is an image of functions via operator with some with similar kind of size conditions, but we've got this kind of condition, right, which is not very explicit, and it's in a sense cannot be if you think about it. So this is kind of like there are too many examples. The theory is too rich. So for this to really have a nice and simple description, right? So here we basically, so we've got this always, once again, we've got all these equivalent definitions via square functions, losing area functions, via maximal functions, and here this is kind of decomposition. And what we would like to do, we would like to have a bit more kind of explicit version of atoms, right, with something which is a bit more similar to that condition rather than the operator being an image via some powers of operators, right? So here our assumptions. So this is kind of explaining what is a dupe transform, by the way. So we assume that function h is harmonic. So if you think about it, this is just assumptions that semi-group preserve this function, right? There are some technical assumptions which wherever kind of doubling is all over the place here. Unfortunately, right, here there's quite a few questions here of non-doubling situations, but that's maybe if I have time, I will comment about this later. And okay, so what we assume is that dupe transform, so this is pretty much, we've got an isometry, right, between our original L2 with respect to some measure mu object, right, and we multiply this by h, and then we've got an isometry with this measure here, right? So with this kind of like with this transform, we assume that after this transform, our semi-group, which is kind of our, of course, this is isometry on between these L2 spaces. So we kind of have a change of variables, so to say, for our operator L. And we assume that the semi-group, which will be kind of like now written down in this form, right, after easy calculation, satisfies upper and lower Gaussian bounds with respect to the new space, or with respect to this weighted measure. So that's kind of explanation of a dupe transform, and this is one of these things which is maybe at the beginning not extremely natural, but if you study heat kernels and theory for long enough, you will kind of believe that dupe transform is the most natural things in the world. Okay. So a simple example. So I kind of like just give here a couple of simple examples for you to have just a taste of what we are talking about, right? So we can talk about here about half line with zero infinity with Dirichlet Laplacian condition, right? And then our harmonic functions will be h of x will be x. Note here that this harmonic function is not bounded, right? And we pretty much, but after dupe transform, right, actually the Dirichlet heat kernel bounds will become a kernel with upper and lower estimates, right? And then another example, again, Dirichlet Laplacian, right, where we consider R3 with excluded ball, right? And here we've got bounded harmonic functions. You can easily check that this is a harmonic functions, right? So here our operators L is just Dirichlet Laplacian, right? With two cases where one is just a half line, and the other one, which is R3 with excluded with a ball. This is maybe not the most exciting examples which I could share with you, but these are the simplest. And actually there's kind of like there is a kind of a bit of a dichotomy here, which I would kind of like to comment soon, that in one case here we've got this harmonic functions which is unbounded, and in the other case we've got a bounded harmonic function, right? So here we are with all these assumptions. We've got a theory which is similar to previous characteristic, right? So we've got still cancellation condition, right? And we have very similar assumptions on support of A. And we've got slightly different, and I want to talk about this. I hope I will have just a minute to talk about this, because this is kind of actually a new thing which I want to add to these things here. Quite recent things which I want to add to this point, but we've got this kind of conditions which are very similar to definitions of Hardy spaces in a classical setting, right? The only difference is that we have here this cancellation condition, and this is kind of interesting. So actually, at least in some of the cases, if you take cancellation conditions against a constant function, right, you've got in a classical case, right, for Laplacian, you can think about h of x, right? So for standard Laplace operator, you can think about h of x being just equal to 1, right? So this kind of explain why you have a cancellation condition just even equal to 1. But here you've got a cancellation condition with h of x, and at least if function h is bounded, then this is a necessary condition, right? And if you take a functions for which this is non-zero, but integral against constants is 0, this function is not going to be in H1 spaces with respect to this operator. So that's the kind of like a difference, right? And if I have a time here, maybe I will talk about this. So with this definition, right, we've got what we want to say, that any of this Hoffman and all definitions, right, of H1 with respect to L are equivalent to this atomic decomposition with cancellation condition with respect to function H, right? And so this is actually somehow quite new. This is a new development. I kind of like didn't actually put all conditions which I kind of have here, but maybe I don't have time for longer discussion here anyhow. So the interesting point here, so here what I think in our definition can be written down in a much more natural way. So here we kind of like, if I go back here, right? So here we've got a definition of a size of an atom, right? In respect with this kind of measures coming from Doob transform, right? So we've got this measure which is kind of mu is multiplied by harmonic function. So that's kind of like a bit object which is natural after Doob transform, but which is not natural for our initial kind of interest, right? Because we are indeed we are interested in say our operators acting initially on our initial space before Doob transform, right? So actually that's a kind of like an interesting point. So that's this condition can be replaced by this just integration with respect to measure mu. So that's kind of, I think, much more natural. And this is kind of like the proof is very simple, but somehow strange. One side is kind of like a little bit of some natural assumption plus just say Holder inequality. And but it's kind of obvious that we will not have well, so one of these norms, so some kind of this kind of condition will imply the other, right? But not vice versa. But then after you apply a maximal function, you will see that after you apply maximal functions, the atom will actually have the same kind of, as a result, the atom will have the same norm the same norm of maximal function for this atom in L1, which is kind of like a bit strange. So you've got kind of starting with somehow slightly different norms, you end up with the same definition of a Hardy spaces, which is, I think, kind of interesting phenomenon here, which, yeah, I guess I'm kind of a bit fast here, but I just want to point out this understanding that this is maybe a little bit too fast. And okay, so one kind of set of examples which we can have. I'm kind of concentrating here on examples coming from Dirichlet Laplacian, right? But I was talking in my simplest example about just R3 with cutoff ball, and here the other possibility is that we just take any domain in Rn. I think I should I skip here. I should. And here I'm okay. I'm a little bit cheating here, so I didn't. But I will. Okay, I will not change it. So I will. We consider here a domain omega, and we assume that omega is regular enough, right? And then with these assumptions, we've got a setting where we can apply this theorem. Okay, so there are examples where there are more than one harmonic function, and this example is kind of like somebody else. I don't remember actually right name. We'll be talking about manifolds with ends today, right? So that's a kind of one natural assumption, and the doubling condition. If you've got a kind of with different dimension, whatever it means, then it's kind of doubling condition is not true. So this is kind of like a big challenge which we don't know how to address. So this is something which I want to briefly mention, and I also want to mention is that yeah, I guess I just should finish, right? How much time do I have? I'm over time, I guess.
Yeah, you're over time, but it's okay. You have in 2 minutes the next talk starts. So when you now wrap up everything, yeah. It's fine.
Okay, so it's kind of like there's an interesting point of comparing our results with description of Chang, Kranz, and Stein. So actually, we've got a different description of atoms, right? Which I don't have time to explain. But the concluding spaces are the same. So it's somehow, well, so I would say that I think that our description is more natural, right? But of course, I guess people can have a different opinion about this. So let me just, I don't have time for this. So let me just few kind of changes, mention few points from bibliography here. So I already mentioned Chang, Kranz, Stein, right? I don't have much time to talk about Dziubański, Preisner, and Dziubański, Zienkiewicz. Pfefferman, Stein is kind of one of the classical kind of definition from Hardy spaces in a classical things. Goria and Salovkost is best kind of, I think, possibly explanation for Doob transform, and the paper which I mentioned quite a few times, Hoffman, Lu, Mitra, Yan, which describe kind of general theory of HP spaces corresponding to self-adjoint operators, abstract self-adjoint operators. Okay, thank you very much. Sorry for
that's
overtime.
Okay. Adam, so please allow me that we move your questions to the coffee break, because in 1 minute, so Hong should please now start. Thanks first, Adam, for the nice talk, everybody. Yeah.
Thank you.
Thank you, Adam.
Thank you.